Welcome to the Creating Custom Primitives for the Intel FPGA Deep Learning Acceleration Suite online training. My name is Carl. In this training, we will cover how to use OpenCL to create custom primitives that works with the provided DLA IP to accelerate convolutional neural network inference tasks on the FPGA. Before we begin, you should already be familiar with the basics of the Intel FPGA Deep Learning Acceleration Suite. If not, please first view the short Programmer's Introduction to the Deep Learning Acceleration Suite online training. Before we begin, let's first review the features of the Intel FPGA Deep Learning Acceleration Suite, or DLA Suite, which is meant to accelerate inference of ConvNets. The Intel FPGA DLA Suite allows users to take advantage of the FPGA without going through the lengthy traditional FPGA development process. The DLA Suite consists of various implementations of the deep learning primitives organized in architectures of FPGA images that are tailored for different types of deep learning topologies, which allows users to implement various networks from LXNet to GoogleNet and variety of other topologies, all without recompiling the FPGA. The DLA architectures implement optimized common deep learning primitives such as convolutions, fully connected layers, rectified linear units or ReLU, local response normalization, max and average pooling, concatenation, and many others. We're constantly adding primitives to the DLA as well. When executing the DLA library architectures, the data between layers stay on the FPGA, and for very deep topologies, data just keeps looping through using or bypassing the primitives that are needed for each layer. The diagram shows this particular architecture implementing CNN primitives on the FPGA in the sequence of convolution or fully connected, and then followed by ReLU LRM pooling. In the architecture, the networks are split into subgraphs, which are mapped iteratively to the sequence in the FPGA for execution. Some primitives in that sequence are bypassable to support different combination subgraphs for the network. Finally, networks that use primitives beyond those implemented in FPGA can be computed with a hybrid CPU-GPU FPGA solution. The Intel FPGA Deep Learning Acceleration Suite is part of the Open Visual Inference and Neural Network Optimization, or OpenVINO toolkit. It's a comprehensive toolkit used for developing and deploying computer vision solutions on various Intel platforms. The OpenVINO toolkit provides a seamless way of accelerating inference tasks on various Intel architectures, which includes CPUs, GPUs, VPUs, and FPGAs. While this training focuses on the Deep Learning Deployment Toolkit part of the OpenVINO toolkit also contains support for OpenCV, an open source library providing common infrastructure for computer vision applications, and OpenVX API, offering extension and support heterogeneous execution across accelerators. We're going to focus on the deployment toolkit part of OpenVINO. The DLDT is used to deploy trained deep learning networks through high-level C++ function calls. There are two components to the DLDT: the model optimizer, which converts and optimizes trained models on various deep learning frameworks and converts them to intermediate representation, and the inference engine, which is the second part of DLDT, which is an execution engine that deploys the network by consuming the IR files through optimized C++ API. Deep Learning Development Toolkit can be targeted for many Intel hardware architectures, which includes the FPGAs. When executing on the FPGA, the software layer part of the DLA suite is invoked, which programs the FPGA with bit streams and is built on top of the FPGA OpenCL platform. Here's what a baseline DLA architecture looks like on the FPGA board. The FPGA will contain the DDR and/or high bandwidth memory, which stores the feature data and the filter coefficients. When performing a convolution, the input feature data is fed through an input mux to the on-chip stream buffer, which feeds the data to the convolutional processing element array. The processing element array performs one layer of convolution and/or fully connected layer in a highly parallel fashion. After the PE array, the data is sent through an activation layer, which typically is ReLU. After that, the data is sent to a crossbar where other operators such as pool or norm are connected. Once all the subgraph computation is done, the output feature data for that layer is sent to the stream buffer again, ready to be sent to another convolution layer. Auxiliary kernels are those functionality that are connected to the crossbar and can be activation or other layers that follow the activation. The baseline DLA FPGA bitstream contains pool and norm as auxiliary kernels. Certain precompiled available architectures also contain element-wise add, prelude, leaky ReLU functionality. Users can also customize their FPGA DLA architecture by adding new auxiliary kernels to the crossbar, and this is the focus of this training. For example, users may want to add new activation that are being created, for example, exponential linear unit, ELU, or scaled exponential linear unit. Users can also add other primitives such as scale, power, absolute value, or whatever else that may be needed in their graphs. If you need to customize the FPGA architecture, the Intel FPGA DLA Suite allows you to select and place a custom collection of pre-optimized primitive and convolution PD arrays on the FPGA. If there are primitives that you need but are not supported in the DLA Suite, for example an uncommon activation function, then you can write custom OpenCL code for those functions and add it to the DLA crossbar through the DLA customization flow. The DLA currently supports two different types of custom primitives: unary operations, for example ReLU and hyperbolic 10 activation functions, and binary element-wise operators, for example element-wise add or mult. We support operations such as scale or dropout, where coefficients are loaded into on-chip memory through configuration registers, or for operations such as batch norm, where there are lots of coefficients per layer that can be loaded from off-chip memory. When you create a primitive for DLA, you need to write the OpenCL kernel for that primitive. And as we've mentioned, unary and binary element-wise operators are currently supported. Other types will be made available in the future. In a unary element-wise operation, for example activation, absolute value, power, you have one 3D tensor input, and the operator will act on each individual element of the tensor separately, which results in an output tensor of the same height, width, and depth as the input. In a binary element-wise operation, for example addition, mult, max, or min, you have two equally sized tensors as the input. The operator will act on both tensor element-wise and produce an output tensor the same size as either of the inputs. Before we talk about the steps necessary to build the FPGA bitstream containing the custom primitives, let's first discuss the software requirements. First and foremost, you'll need the Intel FPGA Deep Learning Acceleration Suite developer package, which contains scripts and templates to execute the build process. If you're targeting one of the Intel programmable acceleration cards, you'll need the Intel Acceleration Stack for development. And if you're targeting any other FPGA board, you'll need the Intel FPGA SDK for OpenCL and possibly the board-specific OpenCL board support package. You'll need Python version 2.7.1 or later, which is needed to execute the scripts. And lastly, you'll need the protocol buffer tools because the architecture descriptions are described in the prototext format. Here are all the steps necessary to build the DLA bitstream. There are just three main steps. First, you'll need to create the custom kernel source file for your primitives. This involves running a kernel creation script that creates an OpenCL source file for your custom kernel based on the template. Then you'll just need to populate the OpenCL file with configuration variables and the actual compute portion of the kernel. The second step is to create a DLA architecture specification file for your custom architecture containing the primitives. This is a prototext file. In this file, you'll describe the crossbar connectivity for your kernel, create kernel parameters, and add the custom primitives to your configuration chain. In the final step, you'll run a script that will automatically build the DLA bitstream based on your kernel OpenCL file and the architectural description. We will examine each of these steps in detail. The first thing you'll need to do is create a skeleton OpenCL source file for your custom kernel. This is done by executing a script and providing the appropriate template. The script will contain basic parameters that are populated for a given custom kernel. You'll need to provide as an argument to the Python script the kernel name as well as a template. There are two templates available, a unary element-wise template and a binary element-wise template. The script and templates are located in the DLA templates directory of the DLA developer package. To run the kernel creation script, first navigate to the templates directory and then execute the script. Remember, you'll need the appropriate version of Python first. There are only two arguments, the template CL file and the name of the custom primitive. In the power example given, we're going to implement a power kernel. This is an unary operator, so we'll specify unary eltwise template.cl as the template and we name it power. Once the script finishes, you'll need to move the generated kernel file to the DLA FPGA source directory prior to building the bitstream. When the DLA executes, each component of the DLA, which includes the processing elements, stream buffer, crossbar, and primitives, all receive configuration information from the instruction read from DDR. This is a very long instruction word, or VLIW. And the parameters included can be various types of conveying information such as input tensor sizes, tiled input sizes, which are how things are vectorized along a given depth or C vector. There's configuration to enable each primitive, as well as layer-specific parameters such as scale or exponent in the power case. Each kernel is required to read this even if the custom kernel doesn't need any custom parameters. For example, you can have an absolute value function with no options, but certain parameters are still needed to compute output size versus input size, as well as how to retrieve data in a vectorized format. To ensure the custom primitives receives the appropriate custom configuration variables, you'll need to populate the primitive's OpenCL source. For standard configuration variables, such as input size or tile sizes, the generated kernel source file will already have it pre-populated, so you don't need to write code to retrieve the value. You'll just need to write the code that uses it in the compute portion. You will, however, have to populate the part to retrieve kernel-specific configuration parameters. First, you should search for to-do in the OpenCL code, then create the placeholder for the variable, and use ifconfig to retrieve the value. In the example, we have a power primitive. To retrieve the exponent that can be customized in a deep learning layer, the kernel will query with ifconfig. First power is the custom primitive name, and the second is the name of the parameter in that primitive. This is specified in the architecture file that we'll discuss later. Next, you'll need to populate the compute portion of the OpenCL kernel. This is the custom part. The kernel template is built for you to not worry about data transfers. The input data is already located in the variable packetIn for unary operations, and packetIn-A and packetIn-B for binary operators. You'll need to assign your computed result to compute result packet. To find a place in the OpenCL code to add the compute, look for to-do, add compute logic in the generated OpenCL code. Here's an example of the compute portion of an absolute value unary element-wise operation. In the code, we make use of kernel-specific K vector, the global Q vector, and P vector to process the data at once using unrolled loops. We retrieve the data from the packetIn variable, perform the absolute value, and set the results to compute result packet. Notice we're required to use the ABS val K vector, Q vector, and P vector configurations in order to simultaneously do K vector times Q vector times P vector number of absolute value operations at the same time. The input data can be used as in the example in the previous slide. This slide shows the relationship between the input tensor, the packet, and the data itself. Data is by default of type data value T, which is not a standard OpenCL data type and oftentimes needs to be converted to float to be operated upon. Data value T is of the data type specified in the architecture description. For example, FP16 or FP11. You can use the data value to float function as in the previous slide, or you can operate on the data directly by using provided functions such as add data value, max data value, and is pos data value. These are more efficient and will create operators in the lesser precision. Now that we have the OpenCL source file populated and placed in the DLA source directory, let's take a look at how to modify architecture description file to accommodate the new kernel and to connect it to the rest of the DLA. The DLA architecture specification file is a protobuf formatted file. All of the provided architecture specification files are located in the DLA arch descriptions directory. To create a custom architecture that contains your custom kernel, it's usually a good idea to first copy the architecture prototext from an existing architecture, then modify the new architecture with a new name as well as to add the custom kernel specific information, which includes parameters, connections, and configuration chain. Let's first add the crossbar connectivity for your custom kernel. The crossbar is where all the auxiliary kernels are connected to each other, as well as to the input from the activation layer, as well as the output to the stream buffer through the input mux, or the output write to DDR. The crossbar is usually not a fully populated crossbar, so you should only make connections where needed to save FPGA logic. Each auxiliary kernel has the option of connecting to the activation kernel through the XBAR in port or any other auxiliary kernel. Each auxiliary kernel can also have outgoing connections to the XBAR output port, which goes to the input mux and the output writer, as well as to other auxiliary kernels. It's important to understand the graph you're executing before specifying these connections. Here's an example of a typical DLA crossbar connection. It's important to understand that if you have two different primitives with different k-vector parameters, then width adaptation module is needed to be inserted to bridge the difference. This is done automatically. In this diagram, since pool can follow activation or norm, we set the pool primitive to receive from XBAR import as well as norm and allow it to write to the crossbar output. Then the norm primitives can receive data from the activation through crossbar import or pool and can also write to the crossbar out. This example is actually a fully populated crossbar, so norm and pool can appear in any order in the executed graph. To understand how to set up a crossbar for a given deep learning graph, let's follow this example with the power primitive. Imagine our deep learning network can be broken down into subgraphs as shown on the top right. We have convolution followed by ReLU activation and then power, and then we have convolution ReLU pool and power sequence, followed by convolution ReLU pool, and finally followed by convolution ReLU local response normalization and max pool. We want to create a crossbar connection that best matches this graph. To build the most efficient crossbar, we will want a connection from ReLU to power. This is accomplished by connecting from the crossbar import to power. We also want a connection from max pool layer to power, while the power output is connected to the crossbar output to be fed to the stream buffer. The pool layer takes input from the crossbar in and norm while able to send data to the crossbar out or to power. And lastly, the LRN has inputs from the crossbar in port and able to send data to the pool layer. Now let's create the crossbar connection in the architecture prototext file that mimics the connection from the previous slide. First, for the crossbar out port, we need to make sure that it takes input from the pool and our custom power primitives. Next, for the local response normalization, it takes input from the crossbar in so data can be sent directly from the activation to the norm. Next, we create the input connections for the pooling layer. As previously mentioned, the pooling layer takes input from activation and from ReLU activation and from norm. Finally, for the power custom primitive, it takes input connections from the crossbar in, which is the ReLU activation, as well as the pool layer. This is our complete crossbar setup in the architecture protobuf file. As we had mentioned earlier, every kernel must read configuration data, and this includes global configurations such as size and tile size, as well as custom configuration for each primitive. The config chain is how these parameters are sent to each kernel, including those connected to the crossbar. In the architecture prototext file, add your custom primitive to the config chain. The exact order does not matter, but it should be near the crossbar for best hardware compilation result. In the screen capture, we added the power kernel to the config chain. Next, you'll need to add information about the custom kernel in the architecture prototext file. This is how information about your primitive can be queried from higher level deep learning software stack. You will need to create a custom aux primitive section for each custom primitive, and it should include several fields. The first 4 are required. You'll need to specify the layer type, and this is the name of the layer in the deep learning framework such as TensorFlow or Caffe or whatever framework you're using. This allows the software to understand what layer your primitives can execute. The name field is a unique arbitrary name given for the custom kernel. Next is k-vector. This is different from the global k-vector, which applies to the processing element array. The k-vector here is specific to the custom kernel and is the vectorization factor along the depth of the input or output tensor for your custom kernel. Next is the type. Specify whether your kernel is unary, binary, or windowed operation. Lastly, if your parameter has custom configuration data, you can set up config parameters. The name of the parameters needs to match a higher level deep learning framework layer parameters so information can be passed down from the software stack. You can set up parameters of several types: float, unsigned int, bool, or int, and in the prototext file just by specifying the name. Lastly, in the architecture prototext file, you should modify global parameters so that your architecture will fit on the FPGA for maximum acceleration. For example, you can adjust the on-chip stream buffer size, the SIMD vector size, which is a depth-wise parallelization, the global K vector, which is the number of parallel filters that can be processed, or even the data type, for example, changing from FP16 to FP11 or other data types. All of this is done in the same .prototext architecture parameter file. Here's an example of the global settings in the architecture parameter file. Set the C vector, the K vector for specific auxiliary kernels, and the precision. To summarize the architecture.prototext modifications, here are all the steps again. First, you'll need to create the crossbar connection for your custom primitive. Add the primitive to the config chain, and add the custom primitive specific parameters, and lastly, if necessary, adjust global architecture parameters. Once the custom primitive OpenCL source and the architecture prototext files modifications are done, you can now build or rebuild the DLA FPGA image. Anytime the prototext architecture file or OpenCL source changes, you'll need to rebuild. Be aware the rebuilding process is lengthy because it invokes the Intel FPGA offline OpenCL kernel compiler, which in turn invokes the Intel Quartus Prime software. To run the build process, just call build.sh along with the path to the architecture description prototext file, as well as the target board and the output directory. In this example, I'm creating a new architecture based on my custom.prototext for the RA10 programmable acceleration card. Once the build completes successfully, you should see a new DLA.aocx file, which is the FPGA bitstream. If you wish, you may rename this file. Use the AOCL program command to program the FPGA with this new architecture, and you can seamlessly now execute inference applications which uses the new primitive. This process is completely compatible with the OpenVINO toolkit. This concludes the training. Here are some additional references which will help you. The information in this presentation are also located in the Intel FPGA Deep Learning Acceleration Suite Compilation and Customization Guide. If you haven't already done so, view the 2 additional online trainings listed here, which will explain how to deploy deep learning inference acceleration on the FPGA using OpenVINO toolkit, as well as basics of how the Intel FPGA Deep Learning Acceleration Suite accelerates inference tasks. Finally, for everything OpenVINO related, visit the OpenVINO toolkit home. One last thing, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and how it might be improved. Thank you very much for attending the Creating Custom Primitives for the Intel FPGA Deep Learning Acceleration Suite, and best of luck with all of your designs.